Greeting friends, today we're going to be looking at modeling and optimization using polynomials. Now we recall polynomials from past experience. That's the sum of variables raised to integer exponents. So we're going to start looking at area, model, area, volume, and other different types of models, and how we can create polynomials that represent these. Now here our situation is we've got an open box. It's a 2x4 meter sheet of cardboard. We're going to have the corners cut and sides are folded to create an open box. So anytime I'm creating an equation or a model for something, it's worthwhile to help and create a picture of something. So we've got a sheet of cardboard that is 2 meters by 4 meters. Let's get that right, 2 meters by 4 meters. And what we're going to do is we're going to cut out those corners. And those corners, think like at the bottom of a shoebox, if we cut those out, whoops, that's the wrong size. If we cut out those corners, then we can fold up our box. So when we get rid of those sides become like little pivot points or folding points where I can fold along those dotted lines, and that turns into an open box. Now, we want to write a function to model the volume of that open box. And so what I want to think about is volume is always length times width times height, or rather not always, but that's the volume of a rectangular prism. Now looking back, we've got length, we've got width, we've got height. We don't know how much we cut out of each edge. So I'm going to give that a variable. I'm going to call that x. Each time we're cutting these squares out of x length each side. So what happens is if we take that 2 meters all the way across, and we cut out that x, and we cut out that x, our length was 2 meters, but we've moved x on each side. So that length is 2 subtract 2x, because it was 2 meters, and we took away an x, we took away an x. Now the width was 4 meters, but we've taken away an x, we've taken away an x. Our width is now 4 meters minus 2x. And when we take those edges and we fold them up, that becomes the height of our box. So the height of our box becomes x. Our volume is length by width by height. In terms of the size of the cut that we made in each corner, our volume becomes 2 subtract 2x, 4 subtract 2x, multiplied by x. That's a polynomial. We've got individual binomial terms. Now we could multiply this and get a cubic polynomial because we have x times x times x. I'm going to leave it just like that. We're going to use this in this word optimization. Going back up top, optimization. We're going to find the maximum or minimum of whatsoever possible for our given model. So we've got this. We can go and we can graph this. So I'm going to take that equation, go to my graph, and there's what we have. So here we've got this curve, and we're looking for the maximum value. Now, if we keep going, we've got a cubic polynomial. There is no maximum. As we go further and further out to the right, our function goes up to positive infinity. But what's a reasonable domain? What's a reasonable value that makes sense? Our domain is the size of the x that we can cut out. So what's the largest value x that we can cut out? Well, if we cut out 1 meter from each side, we'd cut the box in half. So the maximum value we can have is 1 meter. The minimum value that we can cut is, well, 0. So a reasonable domain is anything between 0 and 1, between what makes sense. So going back to my graph, I might look for anything in between 0 and 1. And we can see that if we cut 0 meters, we'd have a volume of 0. If we cut 1 meter, we would have a volume of 0. We want the maximum. So what value for x, what size square should we cut out to take the maximum volume? The function that we've got in the top left there, that's our volume. What I can do is I can look at the curve. In Desmos, I can just tap and see that that maximum, x is 0.423, and the y value, in this case, the v, is 1.54. So we have, if x is 0.423, our volume is 1.54 cubic meters. Now in Desmos, we can just easily tap on that value. In the calculator, this is when you graph the function, you find a suitable window. First, you set the x window. X min should be at least 0. X max should be at least 1. And then we can do zoom fit, zoom 0. That will adjust our graphing window to see everything that we need based upon our inputs, based upon our domain. In the calculator, you're going to go to the calc screen, which is second trace. That's the button to the right, to the left of the graph button. So second trace, the calc menu, you can go down to maximum or minimum, depending upon what we're trying to find. In this case, we found the maximum possible volume of that box happens when we cut out 0.423 out of each side, and our volume is 1.54. We started off, we created a polynomial model, we determined an appropriate range, we created a graph, we found a solution to our problem. Let's try the next one. Here, we're going to enclose a rectangular field. 900 meters of fencing are available to enclose a rectangular field with a singular partition drawn down the middle, one section for sheep and the other for llamas. So draw a picture. What does this look like? We have a rectangular pen or a rectangular field. We're going to put fencing around this, and we're going to have a singular partition, a break, right down the middle. One section is going to be for sheep, one section is for llamas. Now write a function in terms of the width of the field to model the area. Okay, so here's what we're thinking. Area, we have a rectangle. Area of a rectangle is length times width, or base times height. Now our length going across and our width. It doesn't matter if we switch length and width as long as we label it appropriately. And what I'm going to do is I'm going to call this x and I'm going to call this y. So we're going to have x is the width of our field, y is the length of our field. So our area is x times y. Now if I go into Desmos, I go, oh, wait a second. I can't graph in terms of x and y. I need it only in terms of one variable. So here's the challenge, is we need to have this only in terms of x. We need a function a of x where there's just an x, no y. So we need to replace that y with something. What we're going to do is we're going to use what I call a constraint equation. And that's using some other information that we have here. We know that we have 900 meters of fencing. That 900 meters of fencing is the perimeter. Well, it's y, it's another y, it's x, it's a second x, it's a third x. So that 900 meters of fencing is actually accounted for with 2y plus 3x because we have x, 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 that's an x, we have y, we have y. All of that together sets up the two pens, one for our sheep, the other for our llamas. What we're going to do for this is we're going to solve for one variable. So I'm going to solve this for y equals, and that's going to get me 900 subtract 3x divide by 2. I'm calling that my constraint equation because we have some restrictions that implies about our area of a field. We're going to take that y equals, and we're going to substitute it into our area function. So our area, length times width, or x times y, well, y is equal to that 900 minus 3x. So I can make a substitution. We've got x 900 minus 3x divided by 2. That is a polynomial because we have x multiplied by x. Now we could multiply this out and get something in standard form, but I'm just going to leave it in factored form. And what I want to think about is, what's a reasonable domain? Now the shortest x can be is if everything's y. So really the shortest that x can be is 0. What's the longest value that x could be? Well, the longest x could be is going to be if y is equal to 0. And so if y is equal to 0, that means we have 3x makes up the entirety of 900. Or x would be 300 at maximum. So I'm going to use that. Now that I've got my area function in terms of just one variable, we've got a suitable domain. Let's go take a look at the graph. And we're trying to find the maximum value. So we just graphed that just on our home screen on Desmos here, negative 10 to 10. We see this blue line. There's our function. Well, if I zoom out, ooh, we know that this is going to be a parabola, that upside down U-shaped curve, but well, we set our domain was 0 to 300. So I'm going to set my axis to go from 0 to 300. I see it go up, I see the graph come down. So now I can zoom appropriately based upon what I have. We can see that from 0 to 300, we have a reasonable domain to look for our area. And our maximum, we can use the calculator, we can use Desmos, we can use our graphing function to find the maximum. We see that x is 150. And our area is that 33,750 square meters. Now with that, if we know our x value, we can find our y. Y was 900 subtract 3x divided by 2. So that's 450 divided by 2. And that gets us 225 meters for our width, our length. But what we did here was we visualized what we're looking at. We knew that our function, we wanted the area of the field. So area in terms of length and width, or x and y. I used other information to create what I'm going to call my constraint equation, solved that for one variable, substituted in, and then we had our function in terms of one variable. We are then looking for the maximum possible area. So maximum or later minimum, we can go into the graph and look at, using a reasonable domain, what's the maximum value? What's the minimum value? Let's try one more. In this example, we have a right triangle, one vertex on the graph of y equals negative x squared plus 9. So there's one vertex. We have another on the x-axis right there, and we have a third on the positive y-axis right there. Write a function to model the area of the triangle. Okay, so what I'm looking for is, what's our goal? Area of the triangle. So I know that area of a triangle is 1/2 base times height. Looking at our triangle, well, it's upside down or it's left to right, whatever you want to say. I'm going to say the base of my triangle is that side. The height of my triangle is that. Well, this height right there, that's the y value. So my height is really, that's an x. The y value of that coordinate right there. The base is this distance. Well, that distance is the same as that distance. Well, that's really x. So the base is equal to the x value. Now, since we are on a coordinate plane, I can take that, my area of my triangle, I can rewrite that as actually 1/2 x times y. But just like the last problem where we were finding the area of the partition field, we have this in terms of two variables. We need this only in terms of one variable. So we need some way of connecting x and y. I'm going to go back to how we defined that point. That vertex is on the graph of the equation y equals negative x squared plus 9. It's right there. We're given y is negative x squared plus 9. That's our constraint equation in this instance. I'm going to rewrite that as y equals 9 minus x squared. And so the area of our triangle is 1/2 x multiplied by 9 minus x squared. Now that does give us a cubic function once again, but our area, we're multiplying two variables, base and height. Our height just happens to be in terms of x squared. But we've got a function just in terms of x, that base. Now we could multiply that out, but I really don't need it. I can keep it in factored form. We're going to take this, find the dimensions that maximize the area of the triangle. So maximum, sometimes we might be finding a minimum. We're going to go to the graph and find the peak, the highest point. Now, what's a reasonable domain? Since we're talking about underneath this curve here, we are in quadrant 1. Well, the least value that x can be has to be greater than 0. So my domain has to be at least 0. What's the largest value x can be? Well, we might have a triangle that's short, like that. We might have a triangle that's really, really tall, like that. We might have a triangle in between. Now, don't trust the picture. Don't say that that's 2 point something, because honestly, I went into a grapher and I just drew this. Didn't think about anything. But the largest x value would be that distance, since it has to be in quadrant 1. That value, where our parabola intersects, well, that would be 0 equals 9 minus x squared, or that 0 equals 3 plus x, 3 minus x. If I factor, that happens at x equals 3. So the largest value that makes sense is 3 for our domain. That's our reasonable domain. We've written a function, our area in terms of x, and we're looking at a reasonable domain. Now let's go over to the graph. Get rid of that, turn that one on. Here, okay, looking at that, doesn't look like there's a maximum anywhere. But then I remember, oh, that's that old window that we were just looking at. I'm going to go back to my normal window. There we go. So here is our cubic curve. We can see in between 0 and 3, there's a reasonable domain. We've got a maximum in there. The maximum value happens at x equals 1.732. Let's put that there. And our area, because our function is not x and y, even though we are graphing at x and y, our function is the area dependent upon x. So that 5.196 is the area. And square units, whatever we have. We could use our x to find the y value, but it's asking for the dimensions. We've got x, we can find y, and we've got the area. That's what we've got. Good luck. Try out the problems. I'll see you later. Bye-bye.